This is going to be a video focused in on, again, particle kinetics, but particle kinetics only in the normal tangential component. So I've chosen two examples here to work from. It's useful to do a couple examples because a lot of this course is going through and drawing pictures and writing equations and making sure that you understand what your coordinate systems are. And in particular, the biggest thing and the most important skill you need to develop is capabilities of dealing with free body diagrams. Let's start with a problem you saw probably in some form in the course already in a lecture. So, kid on a swing. And this is a problem I hate because eventually you're going to go to conservation of energy. And all of the steps that I take to solve this become a lot easier in that approach. But for now, let's sort of deal with this. What's happening is you have a kid, 27 kilos, and at the instant shown, the kid is at rest at a theta of 54 degrees. You're asked to find the child speed and the tension in each of the two supporting cords when theta is equal to 90. So that would be when this is like this. So the kid starts at some point in the swing, ends up at the other end. Okay, and we're going to do this in t coordinates. So real simple starting point, we need to draw out the kid. We recognize that this sort of complex shape here becomes a particle. Kid is a particle, everything is a particle in this half of the course. You have weight, which is acting downward, and you have tension, which is acting upwards. You also have mass times acceleration normal, which is acting towards the center of curvature, and mass times acceleration tangential, which is acting in the direction of motion. So you've got both of those, that's working out really well, and so we have the full free body diagrams. We also have theta at any particular instant that we're looking at. So if I look at my free body diagram, I can write first of all the normal component. Versus normal equals mass times acceleration normal, twice tension minus mg sine theta equals a mass times acceleration. And the reason why I'm using twice tension is that because I have two ropes. Acceleration normal I've already defined, and you're probably used to this now, v squared over rho. So I have 2t minus mg sine theta equals mass times v squared over rho. I have the tangential component, which is mass times acceleration tangential, mg cos theta. And I've got acceleration tangential then, which is equal to g cos theta. Three unknowns, two equations. And in this chapter, this is something that's going to happen over and over. Next chapter, work energy. In the next chapter after that, when we look at momentum, we'll start to look at ways of getting rid of these unknowns. We're going to use kinematics. And kinematics, we already know that acceleration tangential is v dv ds, but the problem is the kid is swinging. So this kid is swinging down an arc, and we'll make that arc ds is equal to radius of curvature times the displacement d theta. So the integral becomes 0, velocity final v dv, and theta initial, theta final, rho g, which is really mass of the kid. Density, or, sorry, I would have gotten rid of mass at this point. So we could get rid of mass here, sorry. This is over here. So we got acceleration tangential, we got rho g cos theta d theta, and we end up with vf squared rho g sine theta, and theta final, theta initial. The final velocity of this kid is 2.37 meters per second, and if I substitute back in over here, I can calculate the tension, and the tension is 159 newtons in each chord. Not a tough problem. It's a lot more work than it needs to be. This problem could be solved in one step with conservation of energy. And you'll see how to do that in the next chapter. More complex motion, one that's often challenging, not so much because the problem is challenging, is a problem like this. And the problem is more challenging because it's tough to visualize. So I have a turntable, and that red disc is rotating in and out of the screen. And on that disc, I'm going to place a smaller disc. So it's a 1.5 kilogram disc is rotating on a turntable. The disc is attached to the point at the center of the turntable, so I've attached it with the cord. Table rotates quickly and the disc is placed on the turntable. The cord breaks when the tension is some arbitrary number. Here it's 134 newtons. And the coefficient of kinetic friction between the table and disc is mu k equals 0.13. How long before the disc is at a speed with which the cord will break? So I have a counterclockwise rotation. I have a disc. I have lots of things happening here. How do I deal with it? I draw out a really simple free body diagram. And I have three directions. I have normal direction, I have tangential direction, and z, vertical. In the normal direction, I only have the tension because that's pointing in towards the center of curvature. And that's equal to mv squared over rho. Okay, that's good. In the tangential direction, I only have the friction force right here. And that's mu kn equals mass times acceleration tangential. Okay, that's good. And the only term left is the normal force N minus mg. N is acting in the vertical upward direction, weight is acting downward. That's equal to 0. And the only thing I'm given at the beginning is that the breaking tension is 134 newtons. 3 equations, 3 unknowns. I can solve through for the whole thing. And I'm given also that the mass of this is 1.5 kilos. And if you do, you'll solve for a normal force of 14.7 newtons, acceleration tangential of 1.28 meters per second squared, and velocity of the disk of 7.91 meters per second. If I want to know how long it takes, I'm going to have to go back to kinematics. And so the velocity critical is equal to velocity naught plus acceleration tangential naught. This is equal to 0. And the acceleration tangential I just solved for over here is 1.28 meters per second squared. So t is the only unknown because I also know velocity critical, and I end up with 6.2 seconds. So in terms of conclusions, two nice NT examples. First one, really you should do it with work energy and never do it the way I just did it. However, it's useful to just sort of set up the problem and see how the problem is going to look like. The turntable problem, personally, I find them very, very difficult to visualize. And it's really sometimes overwhelming to look at all this motion and then say, what do I really focus on? You only focus on the item of interest. In this case, the disc you're placing on the turntable. And once you do that, then you can solve the problem. It becomes less overwhelming at that point.